Look inside a computer's memory, and you won't find numbers, letters, or pictures. You will just find billions of tiny microscopic switches, either on or off, sequences of ones and zeros. Yet from this incredibly simple alphabet, we can build the entire digital universe, from complex mathematics to high-definition video. Here is how we accurately map the real world into binary. We group these bits together to form values. Using base 2, each position is worth double the last. An 8-bit byte can store unsigned denary values from 0 all the way up to 255. To handle negative numbers, we use 2's complement. The most significant bit becomes negative. So a 1 in the highest column actually means minus 128, shifting our whole range downwards. Binary strings get incredibly long for us to read. So programmers use hexadecimal, base 16, to shrink every 4 bits down into a single symbol. This makes it much easier for humans to spot errors in memory addresses. To store text, we simply agree on a lookup table. The ASCII standard assigns a unique binary number to every English letter and punctuation mark. 7 bits gives us 128 possible characters. But the world has thousands of languages. Unicode extends this system, using up to 32 bits per character. This gives us enough room for every alphabet on Earth, plus all of your favorite emojis. A bitmap image slices a picture into a grid of tiny squares called pixels. We record the color of each pixel using binary. The more bits we use per pixel, the more specific colors we can display. But there is a harsh trade-off. Increasing the resolution or the color depth means storing millions of extra bits. This drastically inflates the file size, which is exactly why high-definition photos take up so much storage. Sound in the real world is a continuous analog wave. Computers cannot store continuous data, so we take regular snapshots of the wave's height. This digitization process is called sampling. The sampling rate is how often we check the wave, and the sampling resolution dictates how accurately we record that height. Higher rates mean much higher audio quality, but again, result in vastly larger files. To stop these files from filling our hard drives, we compress them. Lossless compression looks for repeating patterns and records them efficiently, without losing a single bit of the original data. It is absolutely vital for text and code. For images and audio, we can instead use lossy compression. This permanently throws away data that human eyes or ears wouldn't easily notice. The file shrinks massively, but you can never get the exact original back. At its core, everything from banking software to virtual reality boils down to how cleverly we encode data into bits and bytes, utilizing standards like 2's complement and Unicode. We slice continuous realities like sound and images into discrete, measurable grids. In doing so, we constantly balance the fidelity of our digital meteor against the inevitable cost of file size. And finally, we rely heavily on both lossless and lossy compression algorithms to shrink those massive digital representations, allowing them to travel across global networks in an instant.